So let's look at this problem very close to the idea that we were discussing just before this. Band limited signals with a finite duration. By finite duration, I meant I want pulses. So look at here, this is a pulse because it's of duration t. So anybody, how will its transform look like? Anyone? If it is a pulse. So strictly the transform will be, goes on forever. In other words, the transform cannot be finite. So it cannot be band limited. That's the reason I put it in quote unquote. So if it is a pulse, the Fourier transform shows the bandwidth and the Fourier transform goes forever. But you can see if the signal is a finite energy, look at here, the signal is finite energy. So anyone knows how do you express the energy in Parseval's, in the frequency domain? Parseval's relation, whatever. Yeah, f omega squared d omega. So look here, the energy, but this is from this is the key. This is from minus infinity to plus infinity. This is from 0 to t. But so this quantity is clearly a finite number, right? If it is finite, what will happen to the tails? Anyone? So after some time, the tails have to vanish, right? So it's not like the tail, it cannot pick up later forever. Even if it picks up, it has to go down at some point, right? So it's reasonable to assume that especially when omega is very large, the values have to be, so this clearly shows that f omega has to go to 0 as omega goes to infinity, right? So the best thing we could do is, it cannot be band limited, but what we could, so it's quite possible that most of the energy can be concentrated in a small region. And so if you say that this is the bandwidth where most of the energy is concentrated, so how we could reformulate this question is, given find me a pulse whose energy is mostly within a certain bandwidth. So that's the problem we are going to solve using the ideas we just discussed in the previous case. So we want to maximize this energy. So the goal is to maximize energy within the band minus B0 to B0. So what we want is maximize the energy within B0 to B0 of f omega squared. Remember, where is the freedom? I'm starting with a finite energy. This could be unit energy. So this signal is unit energy. We want to maximize the energy within a band. So where is the maximization going to be? Huh? Just on the shape alone. So remember, we have nothing else other than the shape, because this is our hands are tied. The bandwidth our hands are tied. So we want to sort of squeeze all this here. All the outside the band energy you want to squeeze by shaping the signal. So this is waveform, you can call it waveform shaping. Of course, you can generalize this idea saying that I want to pump in all the energy here into some band also, B1 to B2. So once you get the idea, you can extend it to other problems. So the way I'm going to do this is, let me create this function. So this is a rectangular function, right? So notice that now I can rewrite this in this fashion. So you can see the ideas. I can use that function. So look here. Here it is from minus B0 to B0. Once I bring in this function, I can change this integral back to what? So that's the idea. I can rewrite this in terms of minus infinity, because this multiplied by this is exactly the same as this. Now let me write this as so let me write f omega squared in this fashion, and let me call this to be let's say q of omega. So I have E B naught, which need to be maximized, is q omega f star omega. So anyone? How do you translate this into time domain? So there is a 1 over 2 pi here, right? Not convolution, you can use whatever, Bessel function. So this is the same as this cross integral is if in the frequency domain or time domain, it is the same, isn't it? So this is, so if the inverse transform of this is q of t and the inverse transform of this is f of t, then what do you get of f omega? Anybody? Yes? Huh? You haven't seen this? What is that? That's what I'm saying. Haven't you seen? This is multiplication. This is the Bessel equality or Parseval's relation. Not convolution. Remember, nothing is getting convolved. It's just a this is the cross product in time domain or frequency domain. So for example, if you put Q equal to F, you get the energy in the frequency domain and time domain. Have you seen this? Of course you have seen this. I mean, yeah. No, it's the same thing. This is the, see, now you put Q equal to F, a special case, you get energy, right? I mean, of course, if this is real, then I don't need the star, right? So the easiest way to prove is you substitute here the inverse transform of F, substitute the inverse transform, and then you do some manipulations, right? By bringing in the delta function, etc. Right? All right, so remember this, look at here again the same argument. This is positive, right? Why? Because look at here, we started with positive quantity. So if I put an absolute value here, it makes no difference. I am not taking the absolute value, it's just the positive quantity. So this is less than or equal to square root of ft squared dt and square root of qt squared, right? And you will get equality here if qt is some lambda times ft. And look at here, maybe this is what you were saying. Q of omega is h omega squared f omega. So q of t is what? Anybody? So this is like, says something, two transforms multiplied. So the inverse is convolution. Whatever is the inverse transform of this multiplied by this, right? So this is going to be, but look at h omega. H omega, this is also h omega squared because of this, the way I have drawn, right? So what is the inverse? So the inverse transform of this convolved with, so this is going to be, so what is the inverse transform here? Anyone? Sinc what? Right, sinc is correct. So the inverse transform is 1 over 2 pi h omega squared e raised to j omega t d omega, right? Minus b naught to b naught, right? So that is 2 pi, not 2 pi, that is 2j sine b naught t divided by 2 pi then j t, right? When you do the, remember, when you do the inverse integral, this is e raised to j omega t divided by jt. When you do the top limit minus bottom limit, you get So J cancels, 2 cancels, you bring in a B naught, you get sinc B naught T, right? So this is sine B naught T minus tau multiplied by F tau d tau. But F tau only goes from 0 to T. What? It's a sinc, right? Yeah. All right, so that is QT. So if I put it here, you get so this is back to this equation again. So again it's a kernel, right? Sinc is a kernel, and we look, and you can solve this, discretize and solve it. But as I said last time, or if you make one more substitution, if you call B naught T to be X, B naught tau to be Y, this gives you B naught multiplied by dt equals dx. So look at this. This equation now reads 1 over pi when t is t. So this will become 0 to B naught t sinc x minus y, right? And f of tau is what? Tau is y over B naught. So I'm going to call it f tilde of, so this will become, and f tilde y equals f of x, right? Because f of x is x over B naught, so that's going to be f tilde of x. And x goes from 0 to so the interesting thing is, what is the interesting thing? You only need to solve one equation. It doesn't matter what the value of B naught and T are. See, you just have to solve this dimensionless equation, and then you can go back to your original problem. And so only the time bandwidth product matters. That's the whole point. So if you know the bandwidth and the time, so you solve this equation just for the top limit as the time bandwidth product. Even though, look here, this is time and bandwidth are separately. And if you change this kernel to anything else, suppose you say that instead of this shape, I'm going to take this shape, then of course it won't be as, you will get the inverse transform of this, let's say sinc squared or whatever is the shape of this, but then it won't turn out to be a time bandwidth product. So the clean thing here is that you only need to solve this equation for various values of this constant. And then you get the, so once you solve this for multiple solutions, you can go back to your problem. So what we have solved is how to pack up most of the energy, maximum energy within a given band. So again, if you know that your channel has most of the energy here, then this is one way to design a signal, because you want your channel to interact with your signal, if that's the good part. So if you want it to interact here, and because this is what you want to pick it up, then you should design the signal so that the energy is maximized there. So you can use this in a signal design for waveform shaping. Any questions?